Chapter 9, Electrons in Atoms and the Periodic Table. We'll start out by talking about a disaster. May 6, 1937, the Hindenburg. There's a picture of it. I don't know what the skin was made out of, but it was flammable. And according to your book, that may have partially contributed to the going up in flames like that, but it was filled with hydrogen gas. And hydrogen gas is very flammable. So it made it across the ocean, but as it was landing, that happened. And 36 out of the 97 people aboard died. It was a big tragedy. So what does that have to do with chemistry? Well, why is hydrogen so reactive? Why does it burn so well? What makes it that way? That's what we're going to look into in this chapter. In contrast, we have modern blimps that are filled with helium, because sometimes man does learn from mistakes. We learned not a good idea to fill a dirigible with hydrogen gas. So they fill the modern ones with helium. Helium is inert. Helium does not burn. Helium really just doesn't react with anything. And so the question is, why? Hydrogen and helium are right next to each other on the periodic table. We need a periodic table. Well, they're not. I guess they're right here. Number 1 and number 2. And yet they're very, very different. Hydrogen's explosive and flammable. Helium is not. So we're going to look at a couple of models of the atom that will help explain why helium is inert and why hydrogen is reactive. Other elements are also reactive. If we look at the periodic table, we see that hydrogen is in group 1 or group 1A, and the other elements in that group, lithium, sodium, potassium, these guys are also very reactive. If we look at helium, he's in the noble gas group over group 18 or 8A, and the other elements in this group, in this family, are also very inert. And so there are patterns in the periodic table, and we're going to see how these models and theories and looking at how the electrons and the atoms are structured explains these patterns in the periodic table. So we're going to look at two important models, the Bohr model and the quantum mechanical model. And these are going to explain, again, reactivity and inertness. And they're also going to help us to understand the periodic law, which we talked about back in Chapter 4, which states that when the elements are arranged in order of increasing atomic number, certain sets of properties recur periodically. So the models are going to show us, or help us to understand, how the electrons exist in the atoms and how that affects the properties of the different elements. So the quantum mechanical model came about in the early 1900s. Here's an illustration, not an illustration, photographs of Niels Bohr on the left and Erwin Schrödinger on the right. And here are some quotes. Niels Bohr said, "Anyone who is not shocked by quantum mechanics has not understood it." Erwin Schrödinger said, "I don't like it, and I'm sorry I ever had anything to do with it." Sadly, that is also the feeling of many chemistry students after studying it. Albert Einstein was also involved in the quantum mechanical model of the atom, and one of his comments was, "God does not play dice with the universe." So it's a hard model to understand, and yet it's foundational to modern chemistry. It's the basis for our modern periodic table. It really guides our understanding of chemical bonding, and applications of the quantum mechanical model of the atom are really important in modern life. Computer technology, semiconductors, microchips, all of those things depend on our understanding of the atom based on the quantum mechanical model. Quantum mechanics also helps us to design new drugs, and that's pretty important too. One of the drugs that's been very important in in not curing AIDS because it cannot be cured, but in helping people who are HIV positive to live fairly normal lives in a fairly normal lifespan. One of those drugs was developed using the ideas of quantum mechanics. So it's an important thing. We're not going to understand it completely in this class. I'm not sure that there's anyone who does. I mean, some of these guys that worked on this, they're Nobel Prize caliber scientists. Albert Einstein, probably the most famous scientist ever. He didn't like it, okay? And yet it's really important.